Cool. Okay. Thank you for having me here today. Good morning, good afternoon, and good night to all attendees, depending on where you are. Today, I'm going to talk about exciting AR/VR display research-related potentials in the near future. And the title of my talk is obviously Towards Unifying Display Experiences with Computer-Generated Holography. And my name is Kaan Akşit. I have recently joined University College London's Computer Science Department as an associate professor. And previously, I was a senior research scientist at NVIDIA in the United States, where I helped co-found a research group dedicated to virtual and augmented reality applications. After 6 years in the industry, I moved back to academia with one goal in mind: to help shape young minds and get their attention to tackling a critical problem, the future of displays. My previous experiences include respected institutions around the globe, such as Koç University in Turkey, Disney Research in Switzerland, Philips Research in Netherlands, and RWTH Aachen University in Germany. I'm primarily known in the research community for my contributions to display technology, specifically augmented reality Neareye displays and autostereoscopic displays. Many of my works are awarded by premier conferences in my field, such as ACM's SIGGRAPH and IEEE's VR. In this next slide, I bring you a slide highlighting our most noticeable research work from recent years. Let me quickly summarize what you're going to see in these slides. In 2015, we showed that a simple film placed in front of a display could easily make a Neareye light field display from your smartphone. In 2017, much before leading industries achieved this, we showed that varifocal augmented reality Neareye displays could be a key component in the future of Neareye display, and it can help addressing focus-related issues in Neareye displays. In 2019, we showed that most of the components in a Neareye display could be 3D printed. In 2018, 2020, we showed new foveated displays that are in the glasses form factor, and we also introduced various other means to improve resolution and eyesight of a user using our displays. Sorry, I think I'm hearing some background noise. Can you please mute? Now that I have introduced myself and my work with my collaborators, let's dive into the research section of this talk. Today, I will focus my talk on a real-world problem, the future of display technology. We actually spent more than half of our lifetimes in front of displays, and even right now, we are staring at displays in this remote setting. With more remote interactions, this amount will only increase in the future. My laboratory's scientific motivation is to invent and build the proof of concept futures display system for humans. Indeed, one could ask, what is the current state in displays? What are the challenges in display technology, and how does one build the future of display system? The display industry's primary goal for the future is to paint lifelike three-dimensional visuals within our visual field of view. These future displays will provide real lifelike social interactions while freeing us from flat teleconferences just like this one, and will provide us a never-before-seen opportunity in education and entertainment. And of course, will lead to a new family of businesses and healthcare applications. In the current day, we do not have such technology, unfortunately, and the future's display is a remaining scientific challenge. At best, we can render three-dimensional visuals on a two-dimensional display, and it can only exist in a single plane, at a single focus depth plane. But how do we get to the future's three-dimensional display from these two-dimensional displays that we have? In response, the industry and the academia have been pushing forward with the Neareye displays for virtual and augmented reality applications. These devices are highly sophisticated engineering marvels due to the components involved in making them. And hopefully one day, we will be able to shrink our computers, our optics, and batteries into a pair of glasses form factor so that we can use it on demand in anywhere at any place. But we need to be aware there are just too many problems to tackle at once. if I dive into the explaining these problems to you right now, I'm afraid we will run out of time. But even without talking much about the problems, you can easily state that it's really, really hard to build these devices because it requires an expertise space from including graphics, computer vision, optical sciences, vision sciences, user interface design, mechanics, electronics, and chemical components. And you have to have all of these things in one single body. I should say that we need a way to avoid all these problems you see in this slide. And a solution that either solves or cleverly avoids all these problems remains to be seen. This is an outstanding scientific issue. I argue that there's an alternative way to get around this engineering challenge, but this requires to change our perspectives on the display design problem. Just bear with me for a second. What if we take everything off an Neareye display? I mean, computing modules, light modulators, and batteries. I mean, all the active components. Instead, we pack all these components into projectors and mount these projectors on our walls so that we can beam visuals to a user from a large distance, like 2-3 meters away. In this scenario, a user will only wear passive and lightweight glasses made out of either lenses or mirrors or diffractive components or holographic optical elements. No batteries or no computational units would be needed on the glasses itself. Such a solution will be just like your binoculars. And this way we can avoid really big problems involving Neareye displays, such as heating, form factor, weight, power, and compute-related issues. But there can be other ways that maybe solves this problem, right? So we thought about this and we started looking into all types of augmented reality displays. We looked into retinal, Neareye, handheld, and spatial displays that exist today that are known in the literature. Some of these displays are doing some similar things to our potential here, our potential proposal here, and they project on walls or moving surfaces. But there is no display in the display literature that projects into the eye or into the Neareye device from a distance. To my knowledge, this is the first time such display technology is being proposed. To achieve all of this, the work that I'm going to conduct with my lab is based on computer-generated holography, state-of-the-art in computational display domain. Holography treats light beams like waves, and it promises unique opportunities for being light efficient, high resolution, and can provide you solid state beam steering, so you don't need any mechanical components to steer your beams. In order to achieve something like this, firstly, you have to have a design of a holographic projection display. And using that projection display, you can beam images to users from a large distance, like 2-3 meters away. And our goal here is to invent passive components for users that are thin and lightweight, just like a piece of paper. The mechanisms like accurate beam steering or localizing a user's position with respect to a projector has to be in place in such a scenario so that you can correctly project visuals to a user from a distance. And we have to invent a new algorithmic approach to generate holograms for this dedicated approach. And it has to be fast, reliable, must lead to high quality images at the end of the day. There's a large gap in the literature regarding how light travels across various different distances. And this necessitates basically to invent new light transport models that works across near and far distances so that you can make your calculations and optimization run for your holography. So we also have to marry computer graphics with holograms because obviously in one side there are these holograms, they don't resemble a full image, phase-only holograms. On the other hand, you have this classical computer graphics, everything is drawn using ray tracing and so on. So we have to find a common ground for both of these. I think we need something along the lines of holographic differentiable scene descriptions for rendering purposes. All in all, my description for this new alternative path suggests interesting research opportunities in computer graphics, computer vision, and computational imaging and display domains. If you're curious to learn more about this idea, let's say, please do not hesitate to reach out to me. Surely you can have all the preparations in the world with your ideas and planning in the world, but there's always a risk of failure. So in the last year, I challenged this idea by dedicating my research on this specific topic. So that I can have some sort of sanity checks on what I can do in these terms. We built the first working system of this idea, and it promises a good potential and a good user experience. The first system uses classical optical approaches, meaning it doesn't use computer-generated holography yet. But even without holography, we were able to match resolutions of a current day product, like 8 cycles, 10 cycles per degree, is easily achievable, like over distances like 2 or 3 meters. That's promising because we know that there will be improvement with computer-generated holography, so there is room for improvements, most definitely. And we looked into, identifying new light transport models so that we can make our system work in the future with all the promises that we are suggesting here. And we invented new learned algorithmic approaches. These models are bridging the gap between simulations in holography and the actual experiments. Surely, as you can see in this animation, this enhances holographic visuals in terms of image quality. I should also highlight, it also bypasses the calibration routines that you would have typically in a typical holographic display. So there's some automatization of things that can help with all of the holographic version of this projector. So in parallel, we also identified new ways for generating holograms at different depth levels, and the calculation of these multi-depth holograms are expensive in general. So we looked into making them run faster. I'll skip talking about the details as this work is in preparation, but please stay tuned. We also formulated a library. It is open and public and ready for our work, and you can download this library on GitHub. There's a reasonable amount of documentation included in this library, and it can help you to establish solutions for ray tracing or holography related or perception related problems that you might have in your research lines. In addition, we identified a foveated rendering method which can perceptually guide our routines in the future in terms of how we generate the images for the user. We also published the perceptual guide as a loss function inside the same library, so you can just install this thing and use the loss function at will. For more, please check our work and reach out to me if you're interested, or my collaborators if this sounds interesting to you. Most of these works have been published, and the early evidence is here. All of this work suggests that the idea that I'm proposing has the potential to deliver the promises in the near future. Surely you can question me and say, but what happens if you build such a system? What kind of impact can you achieve with such a system? I think this work's most significant expected contribution will be delivering a practical display design for 3-dimensional visuals. And more complete light transport models will be formulated along the way. And a physical accuracy of computer graphics will be improved with the introduction of holographics. And it will hopefully, crossing fingers, it will also hopefully improve the adoption of AR/VR, and users will benefit from it in the long run. They will have access to new applications for sure. And with the increased adoption, hopefully the further development in the industry will increase, and we will be free to look into the next problem, basically. So after a brief introduction, I argued that displays are essential for our lives. And I also say that all of us see the future in AR/VR. And I promised to remove 95% of the components from the body of a Neareye display and putting it at some other location that is removed. And I provided some evidence with an early prototype. We mount this prototype on a robot arm, beam images from far, and we were able to show that you can project visuals for over large distances. With that, I want to conclude my talk here, and I'll be more than happy to answer your questions. Thank you.